I would like to make a couple of apologies before I start. The first is my slides are very simple. I'm not here to sell boxes. I'm here to sell ideas. And the second is I will not say the word OpenFlow after this first time that I said it. I was going to thank Sanjeev for not saying it, but then he said it a few times, so sorry, well, Sanjeev.
They asked me.
They didn't? You are. So what I want to talk about is the paradigms that we have for SDN. And I want to start with the fundamental problems that we're trying to solve in networks, the operator pain that we see. And then talk about some of the paradigm shifts that we have in our whole approach to networking. And then look at two models of SDN, SDN as an operating system and SDN as a compiler. And then to make this somewhat more concrete, give an example. And in fact, the example will align nicely with what Frank and Elisa talked about. And then, conclude. So the fundamental problems that we see operators talking about, and we see this from multiple operators, and not just in service providers, but also enterprises, also in data centers. We want more innovation in networking. We want to be able to roll out new services, do new things with our networks, and we want to be able to do it quickly. This is a very common requirement that people are saying, our networks have become very rigid. They don't react to things quickly. For us to do new things takes too long. And sometimes it costs too much, not just in time, but also in being able to do it. We have to change too many things to make a new service available. The other thing that we see is I want a lot more control over my network. I want control over where my traffic goes. I want control over services. So the example that Frank talked about, I want to be able to chain things. I want to customize it for a particular user or group of users. So it's, control over devices, control over ports, but really control over traffic and control over services. I want more abstraction. We actually dive too deep too soon, and I want to be able to step back and understand what my network is doing. Actually, sometimes I understand what I think I'm doing, and then figure out what you're really doing. So that's where the last one comes in. We want more visibility, and we want visibility down from the low layer to understand, packets and bytes and stuff, all the way up to what are my services doing, how are my customers actually appreciating my network. So there's a specification of what I would like to see in the network, and there's the actuality what's in the network, and we need to bring them all together. So here are some fundamental problems that we need to solve, we need to tackle, so that operators, whether operators of service provider networks or operators of enterprise networks, or even operators of data center networks, can really be more effective in doing what they need to do. So I think SDN, and yesterday we were trying to define SDN, I don't really care for what the letters SDN stands. I think SDN is really a movement. And the first big thing, the first constructive thing that SDN does is this paradigm shift away from boxes and to the network. We really need to stop thinking about the boxes and ports and things that make up the network, and actually look at the whole network. So the elements that you see in a box today may get pulled out of the box and may get distributed in different ways across the network. They'll all be there, and maybe there'll be new elements, but it's really important that we step away from the box and really look at the network. So in order to examine this paradigm shift, I'm going to look at two models of SDN. The one that most people talk about is the paradigm of an operating system or a network operating system. The one that I'm going to focus on is the paradigm of a compiler. So I'll describe each, and I'll try to score them, and I'll, of course, give myself very high marks, which is, But I will leave it to you to really do the scoring. And then to illustrate the SDN as a compiler paradigm, I will take some examples. So the usual thing that people say with SDN is, I need to separate the control plane and data plane. I'll centralize the control plane. I'll present this control plane as a network OS. In the process, the data plane might become really dumb, but we've seen in Eric's talk, we've seen indications that maybe you don't want it really dumb, but at least the initial paradigm is the data plane becomes really dumb, intelligence goes into the centralized control plane, and this control plane presents some APIs that you can then use to write control programs to place the traffic where you want, to create new services, to create service chains, et cetera, et cetera. The paradigm here is that this network OS will give you the facilities, the services that you need to do all this. And what you're expected to do with this is to write imperative programs that say, do this, do this, do this, and a new service shows up or traffic goes where you want it to go. So essentially, the network OS is like a regular OS, except it's network-wide. It gives you a common view of the whole thing. And where a normal OS would give you scheduling, memory management, and so on, this OS will give you a set of interfaces. We haven't defined them yet, but think of this as a new POSIX, where it'll tell you, here's what your network looks like, here's the topology, here's the current state of different devices, ports, links, and so on. And now I can use this so that I can have access to things across the network rather than looking box by box. And so the control program is thought of as a transformation from the current state of the network, which the network OS presents to me, to the desired state, which might be move the flow from here to there or create a new service somewhere else. And so essentially a control program is a transformation from the current state of the network to a desired state. So the fundamental abstraction that you're working with is the network as an annotated graph. The nodes are the devices in the graph. The links are the connections between these nodes, and they're annotated with different things like capacity or latency or something else. And at the end of this, I look at the whole network as the current state, and then I try to transform it. How do I reason about this? Well, I have control programs, and they're essentially transformations. One of the things, though, is in presenting this model, people said, we don't have enough network abstractions, so we're going to use this as an abstraction. It starts off looking nice, but then when you say my control programs are transformations, and then I'm given two control programs, and you ask me, what is the net result of these two control programs operating on my network state? One of them, yes, it transforms it from here to there. So here's the current state, here's the desired state. The other one says, here's the current state, here's the desired state. When I put them together, can I really reason about this? Do I know what the end state is when I'm running multiple control programs, especially when those control programs are C programs or Java programs that are trying to change the network? How do I know this is correct? Again, it gives you a way to talk about correctness because I'm not talking about boxes anymore. I'm abstracting all this into a common view of the network. But how do I analyze these network transformations? Essentially, I'm going back to program correctness. And I love program correctness, but in the end, it turned out to be a useful way of reorganizing how we write programs, but not really a useful way of proving that programs are correct, because the proofs are often longer than the programs themselves. And as I just said, if I have multiple of these control programs working together, how do I actually anticipate how services interact? I'm trying to offer a video service here. I'm trying to offer a data center interconnect there, and both of them need a lot of bandwidth. How do they interact? Where do they interact? Is there actually a place where I'm causing congestion or latency that one service will affect the other? You can do this, probably. You have to develop a calculus of network transformations and say, this program is doing this transformation, this program is doing this other transformation, here's how they work together. in the end, though, while we're looking for this abstraction, while we're looking for being able to reason and anticipate service interaction, I think this becomes quite hard to do. It's still a lot better than trying to do it box by box. So if I score this and a check mark being, yeah, we did a good job here, and a cross being, we still need to do some work, I essentially say that we want more innovation, we can get more innovation because now we can step away from the boxes in the network and try to do something. But I'm not sure you can do it quickly because people underestimate the difficulty of writing programs and making sure the programs are correct and doing the right thing. We want more control. This gives you more control. But again, it's a very difficult way of getting that control. We want more abstraction. Yes, we have this abstraction of the network as a graph. But how do I understand what I'm doing? By reading a program. Again, I think that's a huge improvement over reading CLI across 100 boxes, but I'm not sure we're there yet. And for visibility, I don't think we've even scratched the surface. So don't get me wrong. I think the people who started SDN did us a huge favor. In some sense, they woke us up from our deep sleep and said, here's things you got to work on. But I think the approach today is too low level, and we need to step back from it. One thing that I enjoyed in Eric's talk was, while he said OpenFlow many times, he did say that people are building higher level approaches on top of that. I just want to start from the top and then go down. So, and as I said, we don't talk about visibility much in this approach. The second paradigm of SDN, the one that I want to talk about more, is SDN as a compiler. And it's not a perfect analogy. People say, what's the difference between an OS and a compiler? If you look at something like Java, it's a system, it's a language, it's a compiler, it's a runtime, it's a whole bunch of things. I think the distinguishing thing that I want to focus on is something that's very high level and something that's declarative rather than imperative. Essentially, you say what you want. You don't say how to do it. Somebody else takes care of how to do it. It's, what people have been talking about so far, programmatic interfaces and control programs and so on, you have to say, do this, do this, do this. Look at this current state of the network, move it to this state. I'd rather go with, give a high-level view of specification of what I want to see in the network, and then have the SDN system go off and do it. And notice that I say SDN system. I don't see this as a single controller. I'm not going to have a long debate with someone from some company asking, where does everything fit? But I do think that there are components here that are centralized, there are components that are distributed, there are components that are more about management, there are components that are about distribution. And the data plane at the bottom is not dumb. I don't think it should be dumb or it needs to be dumb. But the system overall, interacting together, says, oh, you want this to happen? I'll go make it happen. And so this is the paradigm that I think we should explore some more and see how that actually fits in. So the style of SDN, this model, this paradigm, essentially says, I'm going to give you an abstraction of a high-level declarative language. And in that language, you state what you want to see in the network. And I'll give you some examples in a couple of minutes. So the network administrator's job is not to start writing C or Scala or some language, but to write something that says, here's a service I want to create. Here's a service chain that I want to create. Here's a set of users that I want to see having this service chain. The SDN compiler, the SDN system, has to translate these high-level things down to low-level instructions for the boxes. But you'll see that my low-level is actually not low-level. It's the appropriate tool for the particular case. The SDN system will also say, oh, this box has this quirkiness, or this box has this capability. I'm going to take care of that. So it's not I, as an administrator, have to go and say, oh, I'm now on this type of box, I'll do this. On a different type of box, I'll do it a different way. Essentially, that's what the SDN system is supposed to do. I'll say one other thing. We've talked a lot about APIs. We've talked a lot about, I talk about languages. Other people talk about different things. Ultimately, I think the most interesting thing is the data model. And if you say, here's a common data model that everyone can agree on, here are the basic elements of the data model, here are manipulations of the data model. You can express this as APIs, you can express this as a language, you can express it with different bindings for different underlying languages. I think the interesting thing that we should really talk about is data models. So, excuse me, the fundamental abstraction here is this high-level specification. How do you reason about this? I don't know yet, but I think if you try to understand what a bunch of specifications are doing, and the specifications are high-level and relatively short, you have a chance to do this. If the specification is a bunch of CLI on 100 different boxes, you have no chance. And if the specification is, imperative programs, it's still hard. The correctness of a specification, it's hard to say. If the specification is high level enough, maybe the specification is also the requirement, because in the end, it's a declarative language. But it would be nice if you had a requirement specification and an actual specification that says, go do this, and then have a way of matching these. And I think these are things that, from an abstract point of view, we need to explore. To say, did I specify this correctly? Is the customer getting the service that they want? If you don't have requirements, it's hard to say how to do it. So you need a requirements language, and you need a specification language. Anticipating service interaction, and for me, this is a very important thing, because people say that they go configure something and something else breaks, and it's very hard to find out why that happens. If you can't compare or figure out how service specifications interact, you're in trouble. Again, I think what happens is, if you have a high-level specification, and in a short way you can specify something very powerful, you have a real chance at this. But if you say, read these programs or read CLI from 100 boxes, you have no chance. So here's the scoring for this. You know what the answer is, right? I think that you actually have a shot at understanding what your network is doing, getting innovation into your network, being able to do it quickly, because you're not sitting down writing elaborate programs that have to take care of every detail. You really want to do this at a high level and get the compiler to take care of all the details. We have to iterate the compiler, and one of the things that scares me most as a software engineer is if the compiler is wrong. And when you start, that does happen a lot. But if you get that right, you get that right once, now you write specifications and they work. So you can get the innovation, you can get it quickly. You can get control, and I think one of the important things that we have to do is, as we develop this data model, you have to put in the right control features, but you have to do it at a high level. And so you have to balance the ability to do find-and control with the ability to specify it in a way that's independent of a box, a port, and so on. I think you really have a good abstraction here, so you can understand what you think you're doing, but you really still need the visibility to make sure that what's happening in the network is what you expect it to happen. So Sanjeev talked about analytics. I think that's really important. But analytics goes across a lot more than just packets and bytes. It flows, but also logs. The low level, what did my compiler compile into, so that when I start debugging, I can understand that. So at the end of the day, if you have a high-level language where you can express what you want and you can express it succinctly, you can, I think, move really much further forward in networking. So I'll give you a couple of examples. If you were at my talk yesterday, you've seen them. Sorry for that, but I think it's useful to see this for those who haven't seen it. If I want to connect two tenants, and I want to make sure that between the connections, they actually go through a couple of services. So Frank's example is, I have a class of users who want parental control and content filtering. And I have tenant 2, which might be the internet. So between my class of users and the internet, I want to make sure that these services are applied. And usually it's the other way around. You're more interested in filtering stuff from the internet. But whatever. I just specify it as connect tenant 1 to tenant 2 via service S1 and service S2. The compiler is supposed to do the rest. This is what I mean by high-level declarative specification of what you want to see. Under the covers, today what we have implemented is we use VRFs, labels, route leaking, BGP next hops. This is the stuff we use. We don't use the other word that I've already said twice, so I won't say it again. This is, for me, a low-level language. But in talking to people who do services, who know much more about services, especially deep packet inspection and so on, they say maybe the underlying construct should be pseudo-wise. Fine. That's a problem for the compiler. That's not a problem for me as a network administrator. So you take this high-level specification, you compile it down. This box wants it in a certain way. This other box wants it in a different way. You do the right thing. You put these together. One thing that's very important that doesn't come out if you don't think about it is I didn't specify on which box these tenants will connect. I didn't specify on which port they're coming in, on which port they're going out, how this happens. Again, this is a detail for the compiler. If you look at compute virtualization, you say I want a VM. You say I want a big, small, medium, or large VM. You don't get to say I want this kind of NIC card or this kind of storage. You just get to say how much storage you want and what kind of connectivity you want. You don't get to say which server it's going to come on. This is what you do in compute virtualization. But in networks, you say, I'm going to start with this box. I'm going to take this port. I'm going to connect this guy here. I'm going to make sure the traffic comes out of this other port. You're really stuck down in this very rigid world. And we really need to step back.
2 minutes, please.
Oh, sorry. OK. The next example is an example of changing an existing service chain. So I'm still connecting tenant 1 to tenant 2. I still have S1 and S2, but I want to insert S3 in the middle. Well, that's up to the SDN system to make sure this all happens. Again, the details of how the route leaking changes, where the BGP next hops go, that's all for the SDN system. I talked about this to a provider in UK, and they said, look, we've been doing this, but we did it by hand. It was the right thing to do. It was very easy to understand until it became very complex to manage as we got more services and more combination of services. They love the idea that a system will take care of this for them. I won't go through this, but what this is supposed to illustrate is that the language has to be flexible enough to express elasticity, to express ACLs, to express other things. At the same time, you don't want to get too low level. You want to be able to express these in a way that's independent of a box, independent of a particular port. It's all very nice to say we've got this high-level view of things, but at the end of the day, when you start troubleshooting, you go bottom up. So if you don't get the right hooks into visibility, if you're not able to say, I'm going to start from the bottom, I'm going to start from where I think the problem is, and work my way up and find out, did I screw up the specification or did the compiler break? This is not going to be a manageable system. So visibility is totally important. So I want to conclude by saying SDN is in its infancy. We have a lot to learn. We have a lot to develop. The OS paradigm is great. It got us started, got us going. I think the compiler paradigm is an important alternative. And for sure, there are going to be other paradigms. We have to be able to explore these and be free to play with them. In the end, I think what we need is a high-level approach, a declarative approach, and a deeper look at what is called the northbound interface, so that we can really have abstractions in networking, and we can really they can be useful abstractions. Sorry.
Thank you, Kireeti. Thanks a lot. Any question in the audience? Yes?
Frank.
Frank.
Thank you, Kireeti. Very interesting talk. Am I on? Yes. One interesting requirement you didn't mention, and we talked about this before, but cost, is really a key thing from the operator. Yeah. So that should really be, on your marking schedule somewhere. Coming back to the operating system or compiler approach, I suggest we don't want either of those. We really want the compiled application, right, which is simply addressed by an API. So you don't want to focus on any of the lower level features. But on the other hand, the lower level features are not immaterial. Even when you write with a high level language, you're basically relying that there are low level hooks in there that make the high level language very effective. And so, you know, the kind of implementation of that lower layer is critical in the end to deliver some of the features that you ultimately want to implement. Not that you want to individually control it, you just want to talk to the compiled application, neither the operating system nor the compiler. But if you put your hooks at the wrong level, you may not, for instance, get the cost factor or the scalability or the service flexibility or the time to market factors.
Right. Thank you. Good comments. I will say one thing, that the services that you see here, and I think this jives with what Eliza was saying, that this, especially when you go layer 4 through layer 7 services, so DPI, content filtering, and so on, it makes more sense to do those in general purpose hardware than maybe L2 and L3 services, or functions. So these, what you see here as S1, S2, S3, could easily be on a compute node somewhere. And so, to some extent, that answers the cost thing. But I wanted to stay at the fundamental abstraction level. So I wasn't talking about cost, but I think it's very possible. You still need the automation. You still need the ability to create those services. And so if you see, for example, in this example, which I didn't go into, you have S4 replicated multiple times, and you have an implicit load balancer, and you have all that orchestration happening under the covers. So you can get the cost benefits of using x86-based servers for S4 with the replication and with the scale out. So I think that's in there somewhere, but I think as a fundamental advancement in this, I don't start with cost, although I know that's important.
Thank you very much, Kireeti.
Yep.
So the last but not the least in this keynote